all for being here tonight. Truly, it's really wonderful to be able to come here and talk to you guys about a subject that I'm really passionate about. Tonight I'm going to talk to you about women programming and the history of computing. My name is Lucy McGuigan. A little bit about me. I moved to Dallas in 2014 to pursue my master's degree in art history. Graduated in 2016 from SMU with my degree. And around that time, I started to get really interested in thinking about how web and mobile applications could be leveraged to help people of today have interactions with historical objects. Some of the objects that I had studied as an art historian that I was so passionate about, I wanted to think about new ways to help other people have those experiences. And so eventually that interest turned into a more general interest in how software can help us interact with the world that we live in. So in 2018, I pursued this further through SMU's Coding Bootcamp to receive my certification as a full-stack web developer. And today I am a front-end engineer at Alto, which Jordan had the pleasure of introducing. Would be more than happy to talk to you guys about the amazing, wonderful team of people that I work with. If you're interested, just come find me after. So the inspiration for this talk really grew out of a desire to marry my love of historical research with my interest in programming. And so, given that today is International Women's Day, it is a great pleasure to be able to speak to you all today about the women whose contributions were so essential to the early history of the field. So we're going to start our journey today in the 19th century with a woman whose name is pretty well known in the canon of the history of computing, Countess Lovelace, Ada King, who was born in 1815 in London. The backdrop of our story is the Industrial Revolution. This is really a time where machine technology is greatly advancing and really changing the relationship between humans and labor as well. So she has some notable parentage. Her father was Lord Byron, the very famous poet. And interestingly enough, between him and his wife, Lady Byron, there's an interesting theme running through their relationship, which is this idea of a dichotomy between poetry and science and mathematics. And so after Ada was born, shortly after, the two separated, Lord and Lady Byron, and Lady Byron was determined that Ada not succumb to the poetical spirit that she had inherited from her father, so insisted that Ada be tutored rigorously in mathematics from the time that she was a very young child. And interestingly enough, Lord Byron was very resistant to the idea of machinery. He was what we would call a Luddite. And interestingly enough, Ada never really saw this dichotomy. She saw poetry and science as being inextricably linked. And she called the work that she did poetical science. She was really enraptured with the idea that mathematics could help us uncover the greatest truths of nature. And this was one of the primary drives that inspired her to do her work. So, after being tutored in mathematics from a series of tutors, at one point when she's presented at royal court in 1833, she meets a man named Charles Babbage. So Charles Babbage became notable for his production of the difference engine. And so as soon as he was inventing these things, he was showing them off at very elaborate parties. And this was essentially a really early computing device, in many ways more like a calculator, actually. And so what could a difference engine do? A difference engine essentially could be used to compute polynomials. So these things that we think of as the first computers were very sort of elaborate calculators that relied on mechanical workings. And so back during that time, there wasn't the capability to raise numbers to powers and multiply. Everything was based on addition and subtraction. And so the really interesting thing is that if you have a polynomial of nth degree, here we have a polynomial of the second degree, all you have to do is find the nth difference, and you can just work backwards. So if you're trying to imagine how Babbage's difference engine worked, it did this 7 times and backwards. So it could compute polynomials to the 7th degree. But as soon as Babbage was building these inventions, there was 2 of them, differential engine, number 1 and number 2, he started having ideas for a machine that could do much more than one type of mathematical operation. So he conceived of what he called an analytical engine. And he had a great deal of difficulty getting this idea off the ground in terms of funding and support. While the British government had given him funding for the difference engine, they were very reluctant to hand over more money for the production of the analytical engine, so it was in fact never built. However, Babbage did have the occasion to travel to Turin, Italy, and present on his invention. There was a young engineer in the audience, Luigi Menabrea, who wrote an article about what he saw at this presentation. The article was written in French. So, Countess Lovelace has the idea, well, there's this awesome article that discusses this invention in detail. Why don't I translate this so that we can share it with an English-speaking audience? But she did much more than just translate. She added extensive commentary about how she saw this device being used in the future. And so, the historian Walter Isaacson has outlined 3 primary ideas that were really critical to the history of computing that were in Ada's notes. The first is the idea of a machine that could be reprogrammed. So, as we discussed, those difference engines, they could do one type of operation, basically computing the value of polynomials. She saw that the analytical engine had much further capabilities than the difference engines would. The second key idea that she had was that it wouldn't be merely limited to mathematical tasks, that any number of different types of media related to music or to poetry could have a place in the operations of the analytical engine. And then finally, she is perhaps best known for being the author of the first published computer program. And what I mean by that is she was the author of the first algorithm that was specifically written to be used in a computer. And so, what did her algorithm do? So, Ada's algorithm was used to compute the Bernoulli numbers. And if we take a look at this piece of paper, we can see a lot of the features that we see in modern programming. We see variables, we see a sequence of steps, we see recursive operations where things are referring back to each other. And so, in many ways, her efforts to imagine some of the various uses of this machine laid out the future of computer programming. So, very sadly, Analytical Engine was never built. Ada did offer to help Charles Babbage in his efforts to gain support. He declined. And sadly, she died at the age of 35 from uterine cancer. By the accounts, she developed a gambling habit, had to pawn off family jewels. But her legacy is well noted in the history of computing, and she is remembered to this day in a variety of different ways. There is a programming language named after her. We have an Ada Lovelace Day that we celebrate. There's a fantastic comic by Sidney Padua, The Thrilling Adventures of Babbage and Lovelace. I highly recommend it. It's quite fun. And I will say that of all of the figures that I will be speaking of today, she is probably the one who is most remembered in the historical canon. And sadly, it wouldn't be for several decades until more significant advances in actual hardware would be made to allow for more significant advances in programming. So at the turn of the century, the word computer didn't refer to a machine. It referred to a person or a job. i.e. one who computes. And the interesting thing about the human computers of the turn of the century is that in many places they were predominantly women. So the first appearance of the word computer in print is actually a 1892 New York Times ad calling computers to come join the team at the Naval Observatory's Nautical Almanac office. And at that institution, Maria Mitchell was actually the only female computer there, but that was very much an anomaly for the time. And she is remembered today best probably for her discovery of a comet, but computers at institutions like this, their work was very much about calculations. And doing all of the work needed to compute complex things such as the trajectory and position over time of Venus, for example. And so you see in these institutions that there are many where the teams are comprised predominantly of women, and this is for several reasons. One is that they were simply cheaper. They could pay a woman less than a man for that job. And then the second is that there was a dichotomy in the thinking about the work of a computer, which was a rote, mechanical kind of operation, versus the work of an astronomer, for example, which was considered intellectual labor. So there began to be this kind of narrative about the different types of work of men and women. But women were associated with this work of computing. And that has a great deal to bear on how women became such critical figures in the history of programming. So, during World War II, there is a drive to develop more advanced machinery that can run programs. The first, which was Colossus, built at Bletchley Park by the British government, was technically the first computer. However, it was not Turing complete in the sense that it could only run one type of program. And so it was used for cryptanalysis or code breaking, but nonetheless, thousands of women were employed at Bletchley Park at this time, and women programmers were critical to the success of this operation. I'll talk a little bit more in depth about two computers in the United States. So we had the Mark I and the ENIAC. So the Mark I was stationed at Harvard. It was the first electromechanical computer, and the ENIAC was the first electronic computer. So the differences in the structural architecture of these two machines means that the programming of them was very different as well. So you can see here how we have an image of program tape from the Mark I. So what you would have to do is actually punch in little holes to tell the computer how to run the program. And in essence, this was part of Charles Babbage's idea come to life. He was very inspired by the Jacquard loom, which uses very similar technology of punch cards. The ENIAC, on the other hand, was operated entirely with plugs and switches. And so you have a trade-off between these two machines. On the one hand, the Mark I, it takes a while to run the program, but the machine is going to run the same way, run the tape through the machine, same way every time. The ENIAC, on the other hand, had to be reconfigured every single time you introduced a different programming. So what you gained in the speed of the electronic machine, you lost in the time that it would take to set these things up, which would often be up to a day to move all of these giant casings around. So for both the Mark I and the ENIAC, women were absolutely essential to the programming teams. In fact, the ENIAC, the primary programming team, was entirely comprised of women. 6 women, in fact. Those women are Kay McNulty, Betty Jean Jennings, Betty Snyder, Fran Billis, Marilyn Westkoff, and Ruth Lichterman. And these women and their work on the ENIAC, in fact, created a lot of the conventions that we still see in programming today. So the ENIAC was installed at the University of Pennsylvania, which is my undergraduate alma mater, if you were wondering. The ENIAC was overseen by a couple, Herman and Adele Goldstein. And Herman oversaw the construction of this computer, and Adele oversaw the the work of the women computers and was responsible for training them as well. And so these women, these 6 women, were already employed at the Moore School of Engineering, working as computers, and were interviewed to be part of this new project of the first electronic computer. Now, like I said, these women were actively coming up with the programming conventions for this machine as they went. Not only did they have to learn completely new hardware, there was no manual for how to run this thing, they also had to actively invent the methodology through which they would program it. So when I say that their contributions were absolutely essential, they structured the way that we think of programming today. So many conventions that we see today, such as the use of subroutines, so the idea that you can have a function that can be used again and called in various different places and then can be employed in a recursive sense, that's something that they were implementing already at the ENIAC and at the Mark I. The idea of commenting code, the idea of collaboration, these are all things that originated with these groups working on the ENIAC and on the Mark I. So, unfortunately, it's only until recently that the work of the ENIAC 6 has been recovered in the historical canon. One particular story is especially illustrative of this, and that is that when they were going to do a demonstration of the ENIAC, Herman and Adele Goldstein invited the 2 Bettys, as they were called, over to their house for some tea and asked them if they could write a program that would calculate the trajectory of a bullet and use this to demonstrate the workings of the ENIAC to the audience. So the demonstration is scheduled for February 15th, and the 2 Bettys are working away, and there's a bug in the program. The bullet doesn't stop, it just keeps going. So, it's getting late, getting very late in the evening. Betty Snyder, she lives in the suburbs, she has to take the train home, and she decides she's going to sleep on it. And if you've ever had one of those moments when you're stuck in a particularly difficult problem that you're trying to solve in your code, and magically you just wake up with the answer, that's what happened. So the next morning, the demonstration goes off without a hitch, and in fact, the program takes 15 seconds to run, which is actually less than the time that it would take for the actual bullet to stop. So everybody was thrilled with this, very impressed. They handed out printouts. But unfortunately, the way that it was covered in media didn't really give credence to the work that these women had done. And so when you look at the pictures that were published in newspapers, it's the male engineers who are photographed. And even furthermore, the journalists describe the machine as a thinking machine, which completely elides all of the work, the thousands and thousands and thousands of hours that these women put into this effort. So, as I mentioned, Mark I was also being built and operated at the same time. Grace Hopper, which is probably one of the more famous names from this presentation, was part of the staff working on the Mark I. So she and several members of the ENIAC team actually all went after the war to join the team at UNIVAC. So these gentlemen, J. Presper Eckert and John Mockley, they started their own company after some licensing disputes about the ENIAC, which they had designed and built. They decided to start a new company where they built the UNIVAC. And during this time, the contributions of these women was absolutely critical. And like I said, many of the conventions that we see today in programming are those that originated during this time and with these teams. At this time, you also have the Whirlwind 1, which is the first computer that was being used from non-mathematical operations. And Judy Clapp in particular was critical to this team as one of the primary programmers. The team was actually comprised of 20% women. So we will go into a little bit of depth about the contributions of Grace Hopper. She was a mathematics professor originally. She enlisted to the Navy, part of the programming staff for Mark I. And there are several ideas that she had that would fundamentally change the way that we think about computers and how we program them. So while she was working on the Mark I and while she was at UNIVAC, she was a very strong advocate for compilers, and especially for the way that compilers would allow us to write programs in syntax that more resembles English, to make it more democratic and accessible for many people. She was also a very strong advocate for machine non-specific language. As I said previously, the Mark I and the ENIAC, the way that they operated, the way that they were programmed, completely different. And this was in fact the paradigm of the time, is that any new machine, you had to rethink the way that you programmed it to be specific to the specifications of that machine. So while she was at the EMCC, building the UNIVAC, she headed the department that created the first implemented compiler. A compiler had been theorized before and published on, but had not been implemented before. And she also created the first English-like programming language. Another area in which Grace Hopper's contributions were essential was in the development of business-oriented computing languages. So around this time, there's a big push from the Department of Defense. They see that there's a greater and greater need for computing power, and everybody's using these different methodologies for programming. We need a common business-oriented language. And so they convened a group together to theorize about how to handle this problem. There was a short-term committee who was tasked with devising a quick solution. 3 out of the 9 people who served on that committee were in fact women, including Grace Hopper. The actual team that implemented COBOL was comprised of 33% women, 3 out of the 9. And COBOL is a language that, from my understanding, is still used today. I don't know if anyone is anyone in here a COBOL developer? Wow, awesome, fantastic. Still used today in my understanding, a lot of banking and government, legacy applications, and was truly revolutionary for the field at the time. So a talk about the contributions of women in programming would, of course, be incomplete without a discussion of the women at NASA. Now, these women have more recently been recovered in art history, specifically due to the influence of the book Hidden Figures and the movie that came out afterwards. So their stories have begun to be told in the popular narrative, which is really, really exciting. Just to highlight a few of the women whose contributions were really essential. Dorothea Vaughn was the first African-American woman who was a supervisor at Langley. She was a Fortran programmer. And Melba Roy Mouton, who was a major contributor to the documentation for APL, or a programming language. So, at this time, 60s, there starts to be a major shift in the narrative about what a programmer is. And so, there starts to be a sense of panic that there would be an increasing demand for computing, but that the supply of programmers who would be able to fill this demand would simply not be there. And so there begins a change in the rhetoric and the narrative and the professionalization of the field. So you start having institutions have degree programs in computer science. And along with this comes a change in the way that we refer to a programmer and the use of the word software engineer. And so the interesting thing about that term, software engineer, is that all along this history, as you've seen, engineers referred to men. And so by naming this particular career field in this way, it was somewhat of a signal to women that this was not the same field. And so you begin to see somewhat of a decline in the number of women who are programmers. Now, of course, there are plenty of notable figures during this time who made essential contributions to the field. People like Jean Sammet, who was part of the team who developed COBOL, later worked at IBM and was the first female president of the ACM. Someone like Sister Mary Kenneth Keller, she was the first woman in the United States to get a PhD in computer science. She later founded the computer science department at Clark College, which was actually one of the first places where there was a computer science department where it wasn't a large university. You also have people like Mary Ellen Wilkes, who designed the operating system for Link, which was the first home computer. And then you have people like Elizabeth Jake Feinler, who was the principal investigator working on the ARPANET, which was essentially kind of like a pre-internet. She was responsible for knowing where every resource was across the ARPANET, coordinating with the various nodes operating along the system to understand what resources they had and how they could be shared. And you also have people like Radia Perlman, who was the inventor of the spanning tree protocol. And so, of course, this is a very cursory overview of the contributions that women made in this field during this time, through the 50s through the 60s. But I wanted to take a moment to sort of step back and think about how the shifts in this field have impacted what we see today. And so, if you look at the data, it's really interesting. During the 1970s, you see a gradual uptick in the number of women who are pursuing and complete bachelor's degrees in computer and information sciences. But then you see something really interesting in 1984. And in 1984, that's that apex, and then after that, the number goes gradually down and down and down. And some scholars have made arguments about why this is. So interestingly enough, what's happening in 1984? This is the advent of the personal computer in one's home, where people can buy a computer and can learn to program in their home. And some researchers did some qualitative research with women who were pursuing degrees in computer science, and one thing that they learned is that when they heard stories about people who had computers in their home, it was almost always a gift to the male children. And oftentimes, there was a sort of internship-like relationship between the father and a male child, teaching how to program and building up those skills. And many of the women who were entering into college without having this previous experience started to feel like maybe they didn't belong. And so you start to see this gradual decline in the number of women who are pursuing these degrees. Another major factor here is that if you look at the advertising of the 1980s, when personal computers were coming into use, they are many times geared towards men. And so this helps to perpetuate a kind of narrative that, maybe I don't belong. So, of course, this doesn't tell the whole story, because as we know today, there are many different ways that you can pursue a career in this field, right? With the predominance of various online resources where you can teach yourself how to code, with coding boot camps, where you can learn in a more non-traditional setting, outside of a bachelor's degree. But still, as of 2018, last year, only 26% of the individuals who are employed in computer and mathematical occupations identify as women. When you look at the numbers of other traditionally underrepresented groups, it's about 8% of African Americans are employed in these fields and about 7% Latinx. So, what's going on? What can we do? So, I came here to you today to give this talk to try to advance a different narrative about how this field came to be, who were the major contributors to this field. I thank Women Who Code for creating a space like this that fosters an inclusive environment for us to grow and learn and support each other, and for initiatives like Applaud Her, where we recognize the contributions of the women surrounding us day by day. And so it's my hope that, as we move forward, that as we're writing our histories today, we are recognizing the valuable contributions of the full diversity of our population in our field. So with that, I'd like to say thank you so much for being here, and happy International Women's Day.